So in this video, we're going to discuss different ways that we can measure angular velocity. So there's been a bunch of mechanical measurement tools that have been used to measure angular velocity. Those have been mostly developed to control internal combustion engines and gas turbines. We're not going to really go into much detail into those. But what we are going to discuss is the stroboscopic angular velocity measurements, and we'll also discuss electromagnetic angular velocity measurements, and how those work. So stroboscopic angular velocity measurements are pretty neat. What they use is they use a flashing light with a varying frequency is used to measure a set point, and a longer detailed description can be shown in this YouTube video. But basically, when the frequency of that flashing light is halved and the strobe light still syncs with the rotation, the actual rate of measurement has been determined. Okay, so we can also use multiple frequency measurements that may be taken to determine the rotational velocity. All right, so they can use this equation here to do that, where we have omega 1 is the maximum sync speed, and omega n here, is the maximum sync speed, while omega 1 is the lowest measured uh, uh, is the lowest measured sync. Or sorry, omega. Sorry, omega 1 is the maximum sync speed. Omega n is the lowest measured synchronous speed. Okay, so just to prove how this equation works, we'll use it in this example here. All right, so when we have syncing a synchronized source of on our stroboscope, what will happen is the wheel that is spinning will always and has a reflective point at one spot. Every time the light flashes, it will be at that exact position. Okay, so this occurred in from this experiment at these different strobe lights. So these are in flashes per minute. Okay, so we have 1, 2, 3, 4, 5, 6 different measurements. So if we use that equation that we're given, our omega 1 is our maximum speed. So our omega 1 in this case is our 3600. Right? Our omega n in this case is our omega 6, which is going to be equal to 600 flashes per minute. Alright, so we can plug that into our equation, alright, for omega. So omega is going to be equal to our maximum, which was 3600 flashes per minute, times our minimum, or omega n, which is 600 flashes per minute. Alright, we multiply that to the number of measurements we took minus 1 that had the same pattern. Alright, and we can divide that by the difference between our max and our min. So in our case, it's 3600 minus 600. Alright, so what we end up getting here is we end up getting 3000 on the denominator, and in the numerator we end up getting 3600 times 600 times 600 times 5. Now 5 times 600 is 33,000, so these 3,000 will cancel out with the 600 and 500, and we're left with our RPM, which would be in 3600. Right? Alright. Now we could repeat this process. Let's say we only had 5 measurements, alright? So we're starting with 1800 as our max, alright? Alright, so 1800 is our max. That would give us 1800 flashes per minute. Alright, and our min would still be 600. In this case, we only have 5 measurements. Alright, so if we solve for omega in this case, alright, what we'll end up getting is that 1800 times 600 times 5 minus 1 divided by 1800 minus 600. And these are all in flashes per minute. So the numerator would be flashes per minute times flashes per minute. The denominator would be flashes per minute. So we end up getting 1200 flashes per minute times 1800 flashes per minute times 600 flashes per minute times 4. Right? So 600 over 1200 is a half. 1800 divided by 2 is 900. And 900 times 4 is 3600. Right? So you can see no matter which measurements you used, or which set of measurements you acquired. So let's say you started lower and you increased, all right, and you got enough data, you basically could use a smaller number of measurements and still accurately estimate the angular velocity using this method. Okay, all right. And then the second type of measurement system is very similar to the linear velocity measurement system we developed earlier, which uses electromagnetic principles. So in this case, we have the device that we're interested in measuring. We have a toothed wheel that will spin, right? And the revolution of that toothed wheel will cause a change in the voltage across a magnetic coil that's wrapped around a wire coil that's wrapped around a magnet, right? As a north and a south pole. Okay. Now, the major thing you need to know is just that the rotational velocity in this case is proportional to the voltage measured across the coil. Okay. So basically, we monitor the output voltage across the coil. You can correlate that output voltage with the rotational velocity. Okay, so we're done at this point talking about measurement systems that can measure displacement, acceleration, and velocity in terms of both linear and rotary motion. So what we're going to focus in on the next video is how we can use both if we know the rotary velocity and we know the torque being applied, how we can estimate the power being applied in a rotary setting.